Welcome back to Archimedean Student Talks. So we'll be doing this every week. And today we have with us Yannis Wells, who's a part 2 at Trinity. And yeah, everyone who knows Yannis would agree that he just loves algebra and logic. And today he'll be talking about something that combines both. So it's a pretty exciting talk. So over to Yannis.
Okay, so I'm hoping I don't bungle this massively because it's something I'm quite passionate about. And to me, it's something that I feel like is missing from the Part 2 logic course, where we introduce logic as this way of formalizing mathematics. And we're very concerned about, oh, are we formalizing it in a nice manner and so and so? And like we look at how we formalize this particular thing called ZF or Zermelo-Franco set theory. But that's kind of massively underrepresenting what we can do with logic. And sure, in that course, it's a very good course for how we formalize and set up the structure of mathematics, but it's not as good at showing that we can genuinely use this to prove results, like concrete results, that at first you might have no clue might be provable in this way. And it's something that it's kind of something that's inherent in, it's due to restrictions that the formalism imposes on the maths we do. And in particular, the structure that I'm going to be talking about is as a first order structure, which essentially means that when we're talking about objects, we're allowed to quantify over elements of those objects, but not over subsets. The very first part of this talk is going to be a quite quick introduction to how we formalize this, because talking about using it without talking about the setup seems like a bad idea. So we're going to talk about first order structure. And initially we have a language that we're going to mostly fix. Sometimes you change the language, but throughout this, it should be a fixed language, like for each example. And a language will consist of function symbols, relation symbols, and constant symbols, along with an associated arity. And this arity is essentially just how many inputs you have. So if you have a function symbol of arity 2, that's just a binary function like f of x comma y. Or if it's arity 1, that's just f of x. Constant symbols, either you don't assign them an arity or they have arity 0, because they just represent actual constants. And then a relation, because you might have you might have come across binary relations, but you might not necessarily have come across general relations. A relation on a set A is a subset of A to the n. And when we're talking about a relation symbol, the arity of the relation symbol will correspond to this n. And as an example, we have the language of groups, which has the symbol m, which is of arity 2, which when we are talking about specific groups, we interpret as multiplication. I, which is a function symbol, again, of arity 1 this time, and E, which is a constant symbol. And then similarly, we have the language of fields, which has multiplication, addition, a 0, and a 1, which have arity 2 and 2 and the constant symbols. Hopefully everyone is on board with this, and this is understandable. Now, when we want to talk about actual objects, we need to talk about what we're going to call structures. And a structure, how we're going to denote for this script V, is a set, capital V, along with interpretations of the various symbols. For each function symbol f, we have a function f superscript curly v, for each relation symbol, a relation RV, and for each constant symbol, a constant, which is just an element of the set. So a function symbol fv of arity n would just be a function from capital V to the n to v, and similarly a relation symbol is a subset of v to the n. And now, how do we talk about these structures? Because so far, we've just said we have structures. We've got no way to talk about them. So this is, we're going to introduce terms and formulae. Now, feel free to ask for clarification because this might be a bit fast. So terms are generalized function symbols. So essentially, they are function symbols and compositions of function symbols. So as an example, I can have x plus y, where x and y are variables. X times y, and these will be in a particular language, and we could just use the language of fields. We can also have something like 0 plus x. So we're fixing one of the inputs. Or we could have 1 plus 1. And if we have no variables, like this is a closed term. But that shouldn't be too important. Or if we're going into the language of groups, we can have something like this. Not necessarily the easiest to read, but this is, and frequently when studying this, people will do lots of abbreviations, or they will move stuff around. So already here with the x plus y, very technically, if I was being super precise, I should write this as plus x comma y, but that's just very awkward. We all know what I mean when I say x plus y. But these don't actually let us ask questions or impose restrictions, because they're just like, they're essentially just, they're a function. There's nothing that tells us this function must equal anything. So formulae are essentially generalized relation symbols. To start off with, given some terms, P1 to Pn, and a relation symbol R of arity n, R of P1 to Pn is a formula. And that's like a simple way. Again, we still can't talk about so many things because like we're not letting ourselves quantify anything yet, and we're not saying we're not letting us do implication and whatever. So here we introduce quantifiers and logical connectives. So given formulae phi and psi, we also have formulae for all x phi. There exists an x psi. Oops. Phi and psi. Phi or psi. Not phi, and phi implies psi. And this is just an inductive definition. So, for example, I can have phi and psi and psi prime. Oh, I should also say that when we have a relation symbol, we can also have equals. So we can also have like P1 equals P2. That's a formula. So for some examples, if again we're going to the language of fields, I can have x equals y. I can have x equals 1, x plus y plus 1 equals z times w. These are all formulae. Again, neither of the languages I introduced earlier had a relation symbol, but if I want to do something like the language of partially ordered sets, which is essentially which has a relation symbol less than. I can have x less than y, x less than y plus 1 if I want to have something like the language of totally ordered fields, or partially ordered fields even. So these, again, don't have quantifiers yet, but for example, if I can have x equals y implies y equals x. I can have x equals 1 and x equals 0. Like this is, there's nothing so far, like under our traditional, I guess, intuition, this last one here is like a false formula, but we'll get into that a bit later. But these formulae don't inherently have a truth value. I don't have any restrictions saying that 1 must not be 0 yet. But again, there's kind of a problem with these examples, in that they're not actually saying much. A lot of them. For example, x equals y. My x and my y are just totally free. So in order to do this, yeah, so for example, just here, x equals y. I don't have any restriction. It's not imposing any restriction. So in order to impose a restriction, all of the variables that appear need to be bound, which essentially means that they're quantified over. A formula of this form is called a sentence. Now we're going to bring in a notion of truth. So given a sentence phi and a structure v, we say that v models phi, or phi is true in v, written like this, if essentially it's true in the structure. So if what we get when we replace the symbols by their interpretations in that structure is true. So this is a bit vague, and like you can go into a formal definition, but I hope that's understandable for everyone. Feel free to say if you want some additional clarification. So now, if we want to restrict structures and come up with theories, that's what we're going to do. That's what I'm going to introduce next. So a theory is a set of sentences. And throughout this, I will frequently use the word axiom. And an axiom is just one of the sentences in a theory. And given a particular theory and a structure, we say that this structure V is a model of T, written very similarly to the truth thing, which is essentially saying that every sentence in T is true in this. And that's exactly what we mean. If for all sentences in the theory, well, that should be V, this structure models that sentence, so that sentence is true. So I hope this is relatively intuitive. And now we're going to say, bring in a concept of something being satisfiable, which is just if it has a model. Oops. So some examples, well, one example actually. So group theory is the collection of these three axioms. So this first one is the associativity law. This is identity. And this is, sorry, that's inverse. And this is identity. And in this, like a model of group theory is exactly a group. And whenever I have a theory, if I say something like field theory, a model of field theory is exactly a field. And that's how we formalize that. And there are many things we can axiomatize, including, as I just mentioned, fields and graphs, which are two things that, if everything goes to plan, there will be some specific examples in field theory and graph theory. And I'll write ft for field theory and g sub r t for graph theory, i.e. the set of axioms for these theories. And now this is compactness, which it might seem magic. And in order to prove this, you need to work a bit, and you need to start talking about what we mean for proofs, and stuff being provable from a theory rather than just truth. But what compactness says is that a theory T is satisfiable if and only if it is finitely satisfiable. Where finitely satisfiable means that every finite subset of T is satisfiable. Now, this should be the end of the initial prerequisites. We're going to come back and define complete theories later, but first we're going to go on to an example, and that is infinite Hall. So for this, we want Hall's marriage theorem, which says if we have a bipartite graph with its vertex set being A disjoint union B, and for all for every subset A prime contained in A, if we have a finite bipartite graph, the neighborhood of A prime is at least as big as A prime, then we have a matching which saturates A, where a matching is just a selection of disjoint edges. So as an example, if I have, I'm just going to draw a K33, so complete bipartite graph with 3 in each. Then if I pick, say, this edge, and this edge, that's a matching because no two edges share a common vertex. And it also saturates A if A is this, because every vertex in A is a part of at least one edge. So this is the finite case. And you can ask, what about the infinite case? And this is what we're going to prove using compactness. So first, we've got to ask, what restrictions do we need? Now G can be infinite. If we impose that every vertex V in A has finite degree and Hall's condition is satisfied, then we have a matching that saturates A. Here, I'm not going to be super formal. I'm not going to give the precise details. If you want to, I would just recommend, if you really want to, I would recommend genuinely just thinking about it and trying to see if you can do it. But I'm going to give the general idea. So what do? Well, we can construct a particular theory, and this will be in some language. It's not overly important for the idea of the proof, but if you're doing it very precisely, you'll want to specify the language. T should have the following property. T is satisfiable if and only if there exists a matching saturating A. And furthermore, given a finite subset t prime of t. T prime is satisfiable if and only if there exists a finite subgraph H of G with a matching saturating, essentially the restriction of A to H. We can equivalently say there is a finite A prime contained in A, and H is A prime union the neighborhood of A prime. It might be slightly unsatisfying, but I'm going to just tell you that this exists. Essentially, you can write down sets of axioms that cover all of the vertices and all of the edges of those vertices, and saying that for any two edges, they don't share an edge. Once we've found it, this condition here, if we have a finite subgraph H of G with a matching that saturates this, well, any finite subgraph of this form has a matching saturating A prime because it's a finite graph and it satisfies Hall's condition. Hall's proof works for all finite cases. So we have this, and so this finite subset T prime is satisfiable. But then T prime is arbitrary. So this tells us that every finite subset of T is satisfiable, which by the, again, quite hastily mentioned compactness theorem, tells us that T itself is satisfiable, which then tells us that we have a matching that saturates A. And we've proved Hall's condition in the infinite case where every vertex has a finite degree. I feel like I should probably take a quick break to see if anyone has any questions, and I very much welcome them at this point. Now I'm going to move on to introducing another concept in like the building of the structure and studying the structure, which is the concept of a complete theory. Let T be a theory. We say that T is complete if for every, like each sentence, either phi is true in T or not phi is true. Note that if we have a particular model, if we replace this with a model, this is just always the case. Because if we look at a particular model, every sentence has a prescribed truth value. Because we just look at the model and we say, is this true? And we have a specific model. And this is actually quite a strong condition. Like there aren't that many complete theories that are like natural to look at. For the rest of this, I don't know quite how long this takes. We're going to look at a particular, actually, collection of theories. And this is going to be to do with some field theory. So we're going to just let Ft be field theory. Now, we say a field is algebraically closed if every non-constant polynomial has a root. And we can actually axiomatize the theory of algebraically closed fields. And this will be an infinite axiomatization, where each axiom deals with, for example, polynomials of a particular degree. As a quick example, do how I can say every quadratic has a root. So I say that for all A0, A1, and A2, there exists an X such that A0 plus A1X plus A2X squared equals 0. And that says every quadratic has a root. And I add infinitely many of these. and I get the theory of algebraically closed fields, which I'm going to call ACF. I just mentioned complete theories. You might ask, is this complete? I'm free to welcome anyone to say yes or no at this point. No, Path does point out that, so here I should say A2 not equal to 0 implies, in order to ensure that this is genuinely a quadratic. Anyway, theory of algebraically closed fields. This is not complete because it doesn't specify the characteristic. We have algebraically closed fields of every characteristic. It turns out if we include the characteristic, we do in fact get a complete theory. And the way we're going to include the characteristic is we're going to create some sentences, chi p, which is the and chi p is the sentence that 1 plus 1 plus 1 equals 0. And that's p times. And we're going to say that ACF P is ACF union chi p. This is algebraically closed fields of characteristic P. And ACF 0, which is characteristic 0, is ACF union not chi 2, not chi 3, and so on. At this point, it's time to introduce something that I mentioned in the abstract and haven't actually mentioned yet, which is the Ax-Grothendieck Theorem. What this says is that K be an algebraically closed field. Let phi from K to the N to K to the N be a polynomial map, where polynomial map just means that each of the coordinates is a polynomial. This result might be a bit surprising. Then if phi is injective, phi is surjective. This feels like quite a surprising result. And it also might seem quite surprising that we can prove it using the inherent structure of mathematics and this first order structure. For me personally, this result that I just came across it and I loved the proof. But similarly, there might be some people who go, why? Why can we do this? This is wrong. Now I'm going to move on to the proof, which might seem a bit black magic. First, we're going to formulate this in some first order way. So how do we formalize let phi be a polynomial map? Because when we said every polynomial had a root, we did it 1 degree at a time. So we're going to do something similar. We're going to let phi n comma d be the sentence every injective polynomial map from k to the n to k to the n of degree at most d is surjective. Where here I'm saying the degree of the polynomial map is just the maximum of the degrees of the individual polynomials. And this we can formulate in a first order manner. And if we let n and d be arbitrary, and we show that this is true, then this proves the entire theorem. Because given any particular polynomial map, it's like the fact that that one is like the injectivity of that one means it gives it surjectivity is proven by a particular n and d. Now we're going to prove this in characteristic P first. This again might seem like a bit of black magic. So this is complete. So one of these things holds. And note that if we have a particular model of this theory, I know I haven't specifically stated this before, but I'm going to state it now. If we have a model of this theory, and this theory proves something, then that thing will have to be true in the model. So if K is a particular algebraically closed field, we can essentially just ask, is this the case? If yes, then we have this. Again, here is somewhere where I am potentially expecting questions if people feel like this is black magic. So feel free to speak up. I'm going to continue writing, but feel free to interrupt. So we can answer in a particular field. Now, because we're working in characteristic P, there's a particular quite nice algebraically closed field of characteristic P. So we're going to let K be the algebraic closure of FP. And the structure of K is quite nice because K is the union of this. K is this union. And in fact, for any m, K is also this union. Now, given a particular polynomial map from k to the n to k to the n, all of the coefficients lie in f p to the m for some m. So like we find some m which all of the coefficients lie in fp to the m. I'm going to label this phi. So what this means, so phi induces a polynomial map from fp to the km to fp to the km for every k. And now, because phi was injective, this induced map is also injective. Oh, I need to do to the power of n, sorry. So the induced map is surjective. This is just by counting, because fp to the km is a finite field, fp to the km to the n is a finite set. An injective map from a finite set to itself is surjective. Now, we have the following. Phi of k is phi the union fp to the km, which is union of, sorry, forgetting my n's. And we've just reduced the phi as surjective. So because this being true is clearly true if it's true for every polynomial map. Artem, you've asked, like, how do you know that our proof in the concrete field doesn't use some fact that is not among the axioms in ACF? This, no, even that's not quite what I would say. We're not talking about proof. Like, we're talking about truth. This is very much a semantic approach. Like, throughout this talk, I haven't really mentioned about what we mean by a proof in a first order language. And that's because proof and truth turn out to be equivalent. So we're just investigating the truth of a particular fact in a particular field, which isn't anything that's and this is kind of the power of complete theories, that the truth of something in the entire theory is the same as the truth in a particular model. And this particular model is chosen in a particular way that the truth is easy to investigate. And we're investigating it by some other knowledge of this model. We know how these polynomial things work with this particular model. So we don't really need to care about that. But then also what Parth said is also correct in that ACFP is complete, so anything true in that theory must be provable from that theory, which again is an equivalence between truth and proof, which I haven't really mentioned here, which is something if you take a course in first order logic rather than say a model theory course, which will follow from that, you'll learn about. And now there's one final thing to do with this. What about ACF 0? Unfortunately, I'm about to break something that I just said. Here I am actually going to introduce proofs. And all I'm going to say is like proofs are like lists of axioms and some series of rules and how we can manipulate the axioms, with the last line being the thing that we want to prove. And they're finite. So suppose we have ACFP modeling the negation of this. And unfortunately, now I'm going to break this thing about me not using proof and truth equivalence. And I'm going to say, so there is some proof. But this proof is finite. So only uses finitely many of the kinds of P. Pick Q bigger than, say, now pick a Q, prime Q that is bigger than the maximum of these. Then all of these statements are true in the algebraically closed fields of characteristic Q. So this proof works in characteristic Q. So we get that ACFQ but we had the opposite. And that is where I'm going to end this. And I hope that this talk has given you some motivation to look at model theory a bit. It's something that I feel like is probably one of the most fascinating areas of mathematics. And it's got applications where you would not expect them. Well, if you haven't studied it. And that's it. If anyone has any questions, feel free to ask them.
If nobody has questions, then yeah, I'll take this opportunity to thank Yannis. That was a really nice talk, and I'm sure a lot of people will check out model theory after this. And thank you very much to everyone for attending. See you all on Thursday when David will be talking about Riemann surfaces. So that's another exciting part 2 topic. Yeah, thank you very much, everyone.